Picture this. You're watching a pro stock drag race in 1986 and one car keeps winning, not by a little, by a lot. While other racers are rebuilding engines every few runs, this one Ford Probe just keeps hammering down the quarter-mile run after run like it's immune to the laws of physics. The other teams tear their cars apart looking for the secret. They find nothing because the revolution wasn't in the engine, it wasn't in the transmission. It was in something so simple, so basic that nobody even thought to look there: the fuel system. This is legacy motoring, and I spend way too much time thinking about fuel delivery systems and the engineering breakthroughs that quietly rewrote motorsports history. If you're someone who geeks out over the mechanical innovations behind legendary race cars and wants to understand why the cars you love perform the way they do, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now here's what most people don't realize. Some of the most world-changing engineering innovations in automotive history didn't come from massive corporate research departments or MIT-educated teams with unlimited budgets. They came from guys in small shops turning wrenches late at night, asking questions that everyone else had stopped asking. And the story I'm about to tell you is probably the best example of that in motorsports history. This is the story of how Bob Glidden, a farm boy from Indiana who relocated to Oklahoma, created a fuel delivery system so radically different that it made NHRA officials scratch their heads and flip through rule books looking for anything they could point to. They couldn't ban it because technically there was no rule against it. They couldn't copy it because nobody fully understood how it worked yet. And they absolutely could not beat it because while every other team on the grid was fighting fuel starvation at 8,000 RPM, Glidden's engines were getting perfect fuel delivery every single time, run after run, race after race. What Glidden invented in his small Oklahoma shop would eventually become the standard for every high-performance fuel system on the planet. But in 1986, it was so weird, so counterintuitive, that experienced engine builders genuinely called it impossible. They said you couldn't pump more fuel than an engine needed without flooding it. They said you couldn't maintain constant pressure under varying demand. They said a lot of things. Glidden just kept winning. Look, to understand why what Glidden built was so revolutionary, we need to back up and understand what everyone else was doing wrong. Because here's the thing, in 1986, pro stock racing was quietly experiencing a serious crisis that most fans watching from the stands had absolutely no idea about. Engines were getting more powerful. They were spinning faster. They were demanding more fuel than ever before. But the fuel systems that fed those engines hadn't evolved at all. Teams were still running what's called a deadhead system. And the name alone should tell you something about where it ended up. The concept is simple enough. A pump pushes fuel from the tank toward the carburetor. A pressure regulator sits somewhere between the pump and the carb. That's it. End of the line. Think of it like a garden hose with a nozzle on the end. Open the nozzle and water flows. Close it and pressure builds up behind it. Straightforward, right? Sure, until you realize what a pro stock engine is actually asking that system to do. A pro stock engine at full throttle, spinning at 8,000 RPM, needs massive amounts of fuel. We're talking somewhere around 600 pounds per hour of fuel flow. To put that into perspective, that actually means something. That's roughly 100 gallons per hour. That's more than 1.5 gallons of fuel every single minute. The pump has to deliver all of that through fuel lines that are typically just 3/8 to 1/2 inch in diameter, maintaining enough pressure to overcome the carburetor's demands, which in 1986 meant somewhere between 7 and 9 psi. Now that sounds manageable on paper, but deadhead systems have a fatal flaw that nobody was talking about. When fuel demand suddenly increases, like when you absolutely bury the throttle at the start of a quarter-mile pass, the pump has to accelerate the entire column of fuel sitting in the lines all the way from the tank to the engine. Imagine trying to push honey through a straw and you'll get the idea. There's lag. Pressure drops. The engine goes lean for a fraction of a second. In street driving, you'd notice a slight hesitation, maybe a little stumble off the line. Annoying, but not catastrophic. In pro stock racing, where engines are running on the absolute ragged edge of detonation all the time, that momentary lean condition doesn't cause a stumble. It causes melted pistons, bent valves, thrown connecting rods, full catastrophic engine failure. The kind that ends your race weekend and costs you $50,000 before you even drive home. The conventional solution at the time was to just throw more hardware at it. And bigger pumps, bigger fuel lines, higher base pressure. But here's where it gets really interesting, because every one of those solutions created brand new problems. Higher fuel pressure meant fuel could force its way past the needle and seat inside the carburetor, flooding the engine at idle. Bigger pumps consumed more mechanical power, which directly robbed horsepower from the rear wheels. And none of it, not one bit of it, solved the fundamental problem. Deadhead systems simply cannot respond instantly to rapidly changing fuel demands. It was physics working against them, and nobody had stopped to ask whether there was a better approach entirely. Bob Glidden stopped to ask. Born in 1944 in Whiteland, Indiana, Glidden wasn't your typical professional race car driver. He didn't come from old money or racing royalty. His father was a mechanic. His mother worked in a factory. Bob learned engines the hard way, with his hands in his dad's garage, rebuilding motors for local racers who couldn't afford to send their stuff to a shop. By the time he relocated to Oklahoma in the 1970s, he understood engines at a level that went beyond practical experience. He understood the why behind everything. He didn't just know what worked. He knew the specific reason it worked, and more importantly, the specific reason something else didn't. Glidden had been competing in pro stock since 1972, and by 1986, he'd already won multiple NHRA championships. But he wasn't satisfied, and that's the word that matters here. Satisfaction is the enemy of innovation. While other championship-caliber teams were throwing serious money at the fuel delivery problem, hiring outside engineers, importing exotic materials, and essentially building a more expensive version of the same broken approach, Glidden went back to first principles, stripped everything down to a single fundamental question. What does an engine actually need from its fuel system? And the answer was straightforward once you asked it plainly. Consistent fuel delivery at consistent pressure, regardless of how much the engine's demand changes from one moment to the next. The solution seemed impossible under conventional thinking, so Glidden simply stopped thinking conventionally. His idea was so elegantly simple that it's almost frustrating in hindsight. Instead of trying to precisely match fuel supply to demand in real time, which was the impossible problem everyone was chasing, why not massively oversupply fuel and just regulate the excess away? Think about a river and a dam. The river always flows at full volume. It doesn't slow down because the dam is there. The dam just diverts what isn't needed somewhere else. The pressure at the dam stays constant whether you're in a drought or a flood because the system isn't trying to match supply to demand. It's operating at full capacity all the time and managing the overflow. That's exactly what Glidden built for a fuel system. Here's how it worked. A high-volume mechanical fuel pump, capable of flowing 800 pounds per hour, ran continuously. It circulated fuel from the tank, through the fuel rails, and back to the tank in a closed loop. At the end of the fuel rail, instead of a dead end where pressure would build and fluctuate, Glidden installed a bypass pressure regulator. This regulator maintained exactly 8 psi in the fuel rails by bleeding off whatever excess fuel the engine wasn't using and returning it to the tank through a dedicated return line. The pump always ran at full capacity. The pressure never varied. The fuel was constantly moving, constantly fresh, constantly ready. Now I want you to sit with that for a second, because it's genuinely that brilliant. While every other team on the grid was trying to push fuel uphill on demand, hoping their pump could react fast enough, Glidden had fuel circulating like a racetrack. The engine could take whatever it needed, whenever it needed it, and the excess simply kept flowing back to the tank. No lag, no pressure drop, no fuel starvation. Ever. Now, you might be thinking, okay, this sounds clever, but how exactly did the mechanical side of this thing actually come together? Because an idea being elegant in theory and an idea actually working under the brutal conditions of pro stock racing are two very different things. And this is where Glidden's hands-on engineering knowledge made all the difference, because the execution was just as precise as the concept. The pump Glidden selected was a modified Hilborn unit originally designed for IndyCar applications. This was a spur gear pump, not the typical rotor or vane style that most teams were using. The spur gear design had a key advantage. It maintained consistent flow characteristics at varying pressures, which meant the pump's output didn't fall off the cliff when system pressure fluctuated. It was also capable of maintaining flow at pressures up to 100 psi, though Glidden only needed 8. Overkill? Absolutely. Intentionally so. He wanted so much pump capacity that the regulator would always have excess flow to bleed off. If the regulator was always managing overflow, pressure would always stay constant. The pump was driven off the camshaft at half-engine speed, which meant at 8,000 RPM, the pump was spinning at 4,000 RPM, moving 800 pounds of fuel per hour through the system continuously. The fuel rails themselves were custom fabricated from billet aluminum. Glidden specified 5/8-inch internal diameter, which was significantly larger than what teams typically ran. The bigger bore meant lower restriction, which meant lower pressure drop along the rail's length, which meant the last injector or carb circuit saw almost the same pressure as the first one. Each rail fed 4 cylinders through individual lines, routing fuel to the carburetor. The rails connected at the rear of the engine through a crossover fitting, and that fitting housed the bypass regulator. This placement was deliberate. By putting the regulator at the end of the fuel path, after fuel had flowed through the entire rail, Glidden ensured the regulator was responding to the actual rail pressure at the point where carburetor demand was drawing from it. The bypass regulator itself was a piece of engineering beauty, and it's worth explaining in detail because it's the heart of the whole system. Unlike a conventional blocking regulator, which restricts incoming flow to build pressure against the dead end, Glidden's bypass regulator operated on a completely different principle. Inside the regulator housing sat a spring-loaded diaphragm. One side of the diaphragm was exposed to fuel rail pressure. The other side was loaded by a calibrated spring. When rail pressure exceeded 8 psi, the diaphragm deflected against the spring, opening a passage that connected the rail directly to the return line. Excess fuel immediately diverted out of the rail and headed back to the tank. When demand increased and pressure dropped below 8 psi, the diaphragm moved back, closing the passage and allowing pressure to rebuild. The response time was measured in milliseconds. Glidden spent weeks experimenting with different spring rates to find the perfect balance. Too soft a spring and the regulator would open too easily, causing pressure to fluctuate below the target. Too stiff and the system would run above 8 psi at low demand conditions, potentially forcing fuel past the carburetor's needle and seat. The final spring rate was something he arrived at empirically, not through calculation, but through testing and observation. That hands-on knowledge is something no engineering manual can fully replace. The return line was equally critical and equally thought through. Glidden sized it at 1/2 inch internal diameter. Here's why that matters. In normal operating conditions, at idle, when the engine was consuming maybe 5 pounds of fuel per hour, the return line had to carry 795 pounds per hour back to the tank. That's almost the entire pump output going through that return line while the engine is just sitting there warming up. At full throttle with the engine consuming 600 pounds per hour, the return line was still handling 200 pounds per hour bypass flow. Size that line too small and you'd create back pressure against the regulator, throwing off your pressure control. Glidden sized it for the worst case scenario and then added margin on top of that. Now here's where it gets really interesting, and I mean genuinely surprising. The return line had an unexpected benefit that Glidden didn't fully anticipate when he first designed the system, but quickly recognized during testing. Because fuel was continuously circulating through the rails and back to the tank, it never had time to sit in the engine compartment and absorb heat. In a deadhead system, fuel sitting in hot fuel rails on a car that's been idling in the staging lanes on a 100-degree Oklahoma afternoon gets heat-soaked. Hot fuel expands, its density drops. You're suddenly delivering less energy per volume than your carburetor jetting expects. Some of it can actually boil, creating vapor pockets that cause the engine to stumble and misfire right when you need it most. Glidden's circulating fuel never stayed in the engine compartment long enough to get meaningfully hot. The rails were always full of relatively fresh, relatively cool fuel. He took this a step further by installing a small heat exchanger in the return line routing. By positioning the return line where it would see airflow from the car's forward motion, the returning fuel was actively cooled before it re-entered the tank. Cooler fuel is denser fuel. Denser fuel contains more energy per pound. More energy per pound means the carburetor jetting that Glidden had calibrated for a specific fuel temperature was consistently accurate instead of drifting as temperatures changed throughout a race day. This was a free horsepower gain that most people didn't even know existed as a problem, let alone a solution. The return line's connection to the fuel tank was another detail that showed how thoroughly Glidden had thought this through. A 1/2-inch line returning fuel at high velocity into a tank creates turbulence. Turbulence aerates fuel, introducing tiny air bubbles that can pass through the system and cause inconsistent carburetor operation. Glidden fabricated a custom tank fitting that directed returning fuel along the tank wall. allowing it to deaerate naturally before reaching the pickup. The tank had a small internal baffle that physically separated the return area from the pickup area. The pump always drew from calm, settled, bubble-free fuel regardless of what was happening on the return side. Look, I realize this is getting technically detailed, and some of you might be wondering whether all these specifics actually added up to a meaningful performance difference. So, let me give you the numbers, because the numbers are what ended the debate. When Glidden first strapped his Ford Probe to the dyno with the new return fuel system installed, his 500 cubic inch Boss 429 based engine showed a 15 horsepower increase compared to the same engine with the old deadhead setup. Now, 15 horsepower sounds modest for a 1,400 horsepower Pro stock engine. But here's the thing. That 15 horsepower wasn't from any change to the engine itself, it came purely from consistent fuel delivery. The engine was now operating at its designed air-fuel ratio on every single pull, instead of occasionally leaning out and pulling timing to protect itself. That 15 horsepower was always available, but previously being left on the table by an inconsistent fuel system. The real advantage, though, wasn't peak power. It was consistency. Run after run on the dyno, the engine made identical power numbers. The variation that other teams accepted as normal, the run-to-run fluctuation in power output that they compensated for by adding extra fuel and retarding timing as a safety margin, was simply gone. Glidden could now tune to the nice edge because he knew the fuel system would hold that edge precisely. Every run would behave exactly like the last one. Track testing confirmed everything the dyno had shown and revealed additional advantages the dyno couldn't capture. Throttle response was instantaneous in a way the drivers and crew chief alike immediately noticed. Slam the throttle open from any RPM point and fuel was there waiting. No bog, no hesitation, no lean spike showing on the wideband air fuel meter they used to monitor combustion quality. The engine pulled hard from the moment the throttle opened to the moment it crossed the finish line. The spark plugs were the most telling physical evidence. After a full day of testing that included dozens of full throttle passes, the plugs looked almost new. Perfect tan coloration across the entire electrode surface, no white speckling that would indicate lean combustion, no black fouling from overrich conditions. The engine was burning fuel exactly as intended, run after run, with no exceptions. Competitors' plugs from a similar day of testing looked like they'd been through combat. The evidence was right there in the palm of your hand. The 1986 NHRA Pro Stock season didn't unfold like a competitive championship battle. It unfolded more like a lesson, a repeated, emphatic, undeniable lesson that Bob Glidden's Ford Probe was operating in a fundamentally different mechanical universe than every other car on the property. 7 national event wins that year. 7. While most competitive pro stock cars were celebrating when they strung together 2 or 3 wins in a season, Glidden was treating national events like routine stops on a predetermined route. The elapsed times told the story with brutal clarity. Glidden's probe was consistently running in the 730 range at speeds exceeding 180 miles per hour. The rest of the field was fighting to crack 740. In drag racing terms, a tenth of a second is an enormous margin. Glidden wasn't just winning, he was winning comfortably, which in the world of professional motorsports is almost more alarming than winning by a razor's edge. Comfortable wins at the professional level mean something structural is different, not just driver skill or a lucky tune-up. Here's what most people don't realize about what that dominance actually looked like from inside the pit area. The most revealing sign wasn't on the timing board, it was in how the two different camps spent their time between rounds. Other teams, serious professional outfits with experienced crew chiefs and engineers, were constantly working between rounds, checking and rechecking fuel pressure, swapping jets in the carburetor to compensate for pressure variations they'd observed during the previous run, adjusting ignition timing as a hedge against lean conditions they couldn't fully prevent, pulling valve covers to check for any early signs of heat damage from lean combustion events. These weren't bad teams doing bad work. They were competent professionals dealing with the inherent limitations of their fuel systems by layering correction on top of correction. Glidden's crew mostly stood around, not from laziness, but because the car simply didn't require the same level of intervention. They checked tire pressure, they wiped down the car, they talked through conditions with the crew chief. Occasionally, they'd verify fuel pressure with a gauge, see it sitting exactly where it was supposed to be, and put the gauge away. The reliability of the system freed up mental bandwidth and physical time that other teams were burning on fuel system management. That freed up bandwidth went into noticing smaller details, optimizing tire prep, dialing in launch strategy with precision, making the car better in every other area because the foundation was already solid. Now here's the part that gets genuinely fascinating from a motorsports politics standpoint. Other racers obviously noticed. You can't watch someone win 7 national events in a single season without doing some serious investigation. The initial theories among competitors were all pointed in the wrong direction. Most assumed Glidden had found some exotic fuel additive or secret carburetor modification that NHRA hadn't caught yet. At multiple events that season, the probe was subjected to post-win technical inspection that went well beyond the standard procedure. Inspectors literally disassembled his carburetor looking for hidden passages or non-stock components. They checked his fuel samples against other competitors. They measured everything that the rulebook gave them authority to measure. They found nothing because there was nothing to find. Every component on the car was legal. Every measurement was within spec. The NHRA rulebook in 1986 was remarkably thin on fuel system regulations. The rules required a fuel tank, fuel lines of adequate construction, a fuel shutoff valve, and some basic safety provisions. That was essentially it. The document said nothing about return lines, nothing about bypass regulators, nothing about circulating fuel systems. Glidden had read the rulebook, identified a space where innovation was completely unconstrained by regulation, and walked right through that door. Warren Johnson was the first competitor to actually figure it out. Johnson, who was himself a genuine engineering mind and Glidden's most formidable rival during this era, was at a race in Dallas when his crew chief noticed something during a close inspection of the probe in the staging lanes. There was an extra line running from the engine compartment area back toward the fuel tank. The initial assumption was that it was some kind of crankcase ventilation or oil drain line. But during warm-up, when a crew member noticed fuel dripping from a fitting near where the line connected to the tank, the pieces clicked into place almost simultaneously for several people in Johnson's camp. Johnson immediately began developing his own return-style fuel system. But he was months behind Glidden in development, testing, and refinement. By the time Johnson's system was race-ready and dialed in, the 1986 season was effectively over and Glidden had the championship. The following season saw rapid adoption across the field as word spread, and the technical magazines started publishing detailed explanations of how return systems worked. Companies that had been manufacturing conventional fuel system components scrambled to develop return-style products. Aeromotive, Weldon, and other performance fuel system manufacturers began offering complete return kits aimed at pro stock teams. What had been Glidden's exclusive competitive advantage for the better part of a season became the accepted standard almost overnight. And this is actually a pattern you see repeatedly in motorsports history. A single innovator operates with a significant advantage, sometimes for an entire season, sometimes longer. Then the secret gets out, everyone adopts it, and the baseline shifts permanently upward. The innovator rarely maintains the edge forever, but their contribution permanently raises the floor for everyone. Here's the thing about what happened next that most people don't discuss. While everyone was busy copying Glidden's first-generation return system and celebrating how much better their cars ran, Glidden was already several steps further down the development path. That's the mark of a genuinely innovative mind. You don't celebrate your innovation while competitors catch up. You use the time they spend catching up to create the next gap. His second-generation system incorporated an additional pressure management strategy downstream of the main bypass regulator. This addressed a subtler problem that only became apparent once the basic return system was working perfectly and he had enough data to see finer details in how the carburetor was behaving. At certain operating conditions, particularly during rapid throttle changes, the pressure differential across the carburetor's fuel circuits would vary slightly as the bypass regulator responded to demand changes. This variation was tiny, far smaller than anything a deadhead system experienced, but Glidden could measure it, and measurement meant he had to address it. He experimented with different return line routing configurations, discovering that a slight consistent upward angle in the return line prevented vapor from accumulating in high points and causing intermittent flow disruptions. He tested different bypass regulator spring rates for different weather conditions, building a catalog of tuning knowledge that his competitors, even after adopting the basic concept, didn't have. He developed specific procedures for priming the system before startup that ensured fuel was circulating at stable pressure before the engine fired, eliminating any variation in the first few seconds after startup. Every one of these refinements was small individually, Collectively, they represented the difference between understanding a concept and mastering it. The broader impact of what Glidden demonstrated in 1986 extended far beyond the pro stock class. NASCAR teams running carbureted engines at super speedways adopted return-style fuel systems within a season or two, setting improved consistency during long green flag runs and better behavior in the high heat conditions of engine compartments running for hours instead of seconds. Sports car racing teams discovered that return systems eliminated fuel starvation during extended high-G cornering situations where fuel could slosh away from the pickup in a deadhead system under sustained lateral loads. Even in the weekend bracket racing community, grassroots racers started seeing the articles in the magazines and building their own return systems from off-the-shelf components. But the impact that reaches furthest, the one that connects directly to you and every car you've ever driven, came from a different direction entirely. By the late 1980s and early 1990s, the automotive industry was transitioning rapidly and somewhat forcibly away from carburetors and toward electronic fuel injection. This transition was driven primarily by emissions regulations that carburetors simply couldn't meet with sufficient precision. EFI systems can control air-fuel ratio with a level of accuracy that a carburetor, no matter how well tuned, cannot match. But EFI introduced a new technical requirement that deadhead systems were completely incapable of meeting. Electronic fuel injectors are fundamentally different devices from carburetor jets. A carburetor jet's flow is determined by its physical size and the pressure differential across it. Change the pressure, change the flow in a predictable and relatively forgiving way. An electronic fuel injector's flow is determined by how long it stays open, measured in milliseconds, times a flow rate that is extremely sensitive to the pressure across the injector. Small pressure variations cause significant and difficult to predict changes in actual fuel delivery. If the engine management computer commands a specific injector pulse width based on a target fuel pressure and the actual pressure at that injector is different, the engine runs at the wrong air-fuel ratio. The computer can't compensate fast enough for rapid pressure variations in a deadhead system. This is where Glidden's return system concept didn't just transfer to EFI, it became mandatory for EFI. Every properly designed electronic fuel injection system maintains a constant reference pressure at the fuel rail using a bypass regulator and return line. The injectors always see the same pressure, so the computer's pulse width calculations always produce the intended fuel delivery. Without this, EFI simply doesn't work with sufficient accuracy to meet modern emission standards or provide the drivability that consumers expect. Your daily driver is almost certainly running some version of what Bob Glidden built in that Oklahoma shop in the mid-1980s. The names on the components are different. The materials are more sophisticated. The pump is probably electric and mounted inside the fuel tank rather than mechanical and driven off the camshaft. But the fundamental operating principle, oversupply fuel with a bypass regulator maintaining constant rail pressure while excess returns to the tank, is identical. Every time you turn your ignition key and your fuel pump primes the system before startup, every time your engine responds instantly to throttle input without hesitation, every time your fuel trim stays stable across different temperatures and altitudes, you're benefiting directly from what Glidden figured out while trying to win drag races. Now, you might be thinking that this seems like an obvious solution in hindsight. And that reaction, that feeling of it being obvious once you hear it explained, is actually one of the most important things to understand about genuine innovation. The deadhead approach wasn't obvious to the people using it in 1986. It wasn't that they were stupid or lazy. They were experienced, talented, motivated professionals with real competitive incentive to solve exactly this problem. The deadhead system was the approach that had been handed down through the tradition of how fuel systems were built, and tradition has a powerful gravitational pull. It takes an unusual combination of curiosity and willingness to question fundamental assumptions, to step back from what everyone does and ask whether what everyone does is actually right. Glidden had that combination in unusual measure. And the reason he had it probably traces back to where he learned his craft. He didn't learn fuel systems in a formal engineering program where certain approaches are taught as correct. He didn't learn them from working at a major automotive company where existing systems represent enormous sunk costs and institutional momentum. He learned them by tearing apart engines and putting them back together in a garage, understanding each component on its own terms, building a mental model of how everything worked from first principles rather than from convention. When you understand something from first principles, you're much more likely to notice when the conventional approach contains a fundamental logical error. Let's talk about the actual financial stakes involved, because that context matters for understanding how significant this innovation was. In 1986, a competitive pro stock engine cost somewhere in the range of $50,000. That's the engine alone, not the car, not the trailer, not the crew, not the entry fees. A catastrophic failure caused by fuel starvation could destroy that engine in a single pass. Teams that were running deadhead systems and pushing their engines hard were losing engines at a rate of roughly 1 per 3 or 4 race weekends. Some teams lost 2 or 3 engines in a single season, which represents a direct out-of-pocket cost that could exceed $150,000 just in engine rebuilds. Glidden's return system, the entire package including the pump, regulator, custom rails, lines, and fittings, cost approximately $1,700 in 1986 money. Adjusted for inflation, that's roughly $4,500 in today's terms. The prevention of a single engine failure paid for the system many times over. But the economic advantage ran deeper than just preventing catastrophic failures. Consistent fuel delivery means consistent combustion temperatures and pressures, which means far less wear on every component in the engine. Pistons, rings, valves, valve seats, bearings, all of these parts live longer when combustion conditions are stable and predictable rather than occasionally spiking to dangerous lean conditions. Teams running Glidden's system could go longer between rebuilds, even on engines that didn't suffer obvious failures. An engine that was rebuilt every 6 race weekends under the old system might go 10 or 12 weekends with equivalent rebuild costs under the return system. Across an entire season, for a well-funded pro stock team competing at a dozen or more national events plus divisional races, the cumulative savings were staggering. It's not an exaggeration to say that the return fuel system was the highest return on investment modification available to a pro stock team in 1986. Not the exotic cylinder head, not the custom crankshaft, not the titanium fasteners. The $1,700 fuel system that prevented engine-destroying lean conditions. Here's what's interesting about Glidden's championship-winning 1986 Probe from a legacy standpoint. The car became so famous that Ford used it extensively in their advertising and promotional materials throughout the late 80s. Ford had been struggling to establish any meaningful motorsports credibility during this period, and a car carrying their name winning 7 national events in a single season and an overall championship was invaluable marketing. The advertising was careful though. Ford's marketing materials talked about the engine, the driver, the engineering excellence. They didn't specifically highlight the fuel system, partly because explaining a bypass pressure regulator doesn't fit neatly into a 30-second television spot, and partly because the return fuel system worked just as well on a Chevrolet or a Mopar as it did on the Ford. It wasn't a Ford innovation. It was a Glidden innovation that happened to be housed in a Ford body. The 1986 Probe eventually found its permanent home in the Motorsports Hall of Fame, where it sits today with the return fuel system intact and functional. It's not just a display piece. It's a working document of engineering history. Anyone who understands what they're looking at can trace every line and fitting and see exactly how the system works. The bypass regulator at the end of the fuel rail, the return line running back to the tank, the custom pump drive arrangements off the camshaft, the oversized fuel rails with their internal dimensions, optimized for minimal restriction. It's all there, completely visible, completely understandable, and completely profound once you know the story behind it. The technical specifications of that championship system are impressive even when measured against modern high-performance builds. The Hilborn spur gear pump Glidden used was rated at 880 pounds per hour at 100 psi test pressure. In actual use at the 8 psi rail pressure Glidden ran, it was effectively limitless from a flow standpoint for its application. The bypass regulator could handle flow rates from near zero all the way to 800 pounds per hour while maintaining 8 psi plus or minus 0.2 of a psi plus. That 0.2 of a psi variation is what's called the regulation precision, and it's extraordinarily tight for a passive mechanical device with no electronic control. The entire system, pump, lines, regulator, rails, return plumbing, and all fittings weighed 18 pounds. 18 pounds for a system that fundamentally changed how an engine performed and how reliably it survived. The return line alone was capable of flowing 3 gallons per minute when fully open, which it essentially was during idle and low-demand operation. Total system fluid capacity, including the fuel tank, all connecting lines, and the rails, was 12 gallons. From a packaging standpoint, the entire additional complexity of a return system over a deadhead system amounted to one additional fitting on the tank, one bypass regulator, and one return line. The weight penalty was under 4 pounds compared to a deadhead system. The cost premium was real but modest. The performance and reliability benefit was transformative. Installation wasn't plug and play though. Glidden understood things about the system that weren't obvious from looking at the components. The pump had to be mounted at or below the level of the fuel tank outlet to maintain prime. If the pump ran dry even briefly, the gear surfaces could be damaged, and damaged gears meant inconsistent flow. The return line needed careful routing to avoid proximity to exhaust components, not just to protect the line from heat damage, but because hot fuel creates vapor pockets, and vapor pockets interrupt consistent flow. Every fitting in the system had to be absolutely leak-free. At full pump output, a significant fitting leak would empty the fuel tank in a matter of minutes. And in a race car environment with hot exhaust surfaces nearby, that's not just a performance problem, it's a fire hazard. These installation details were things that teens copying Glidden's design from magazine descriptions sometimes got wrong. A return system with a slightly incorrect pump mounting height, or a return line that ran near an exhaust header didn't work as reliably as Glidden's, and teams that had problems sometimes blamed the concept rather than their execution. This created a period of mixed results in the broader community, even as the fundamental idea was being validated repeatedly by the teams that got the installation details right. Here's something that gets overlooked in most discussions of Glidden's innovation, and honestly, it's one of the most psychologically interesting aspects of the whole story. The competitive advantage of the return system wasn't purely mechanical. There was a significant psychological dimension to it, and in professional motorsports, psychological factors are rarely trivial. Consider what a race weekend looks like for a pro stock team competing at the professional level. You arrive Thursday for a major national event. Friday is qualifying. Saturday is qualifying again, plus potentially early eliminations depending on the event format. Sunday is the bulk of the elimination rounds building toward the final. From Thursday to Sunday, the team is making multiple full-throttle passes, making decisions between rounds about how to adjust the tune-up based on changing weather conditions, track temperature, and what the data from the previous run showed. The mental load on the crew chief is enormous. Every variable that can be held constant represents cognitive bandwidth that can go toward variables that actually require attention. With a deadhead fuel system, fuel pressure was a variable that could never quite be held constant. It varied with temperature. It varied with the pump's condition and wear state. It varied as the fuel level in the tank changed. The crew chief was always managing fuel pressure in the background, always asking whether the pressure they saw this run was the same as last run, always adjusting jets or timing slightly to compensate for pressure they couldn't fully control. This background management consumed mental bandwidth continuously throughout the weekend. With a return system, fuel pressure was effectively a constant. You verified it at the start of the weekend, and barring a mechanical failure, it stayed there. The crew chief could remove fuel pressure from the list of variables requiring active management and focus entirely on the things that actually change meaningfully: weather, track conditions, tire behavior, staging strategy, driver feedback on how the car felt. The psychological relief of eliminating a persistent source of uncertainty can't be quantified in horsepower, but experienced motorsports professionals will tell you it's real and it matters. Glidden himself, in interviews he gave throughout his career, often talked about the importance of simplifying the variables. His philosophy was to find every source of inconsistency in the system and eliminate it, not manage it, eliminate it. The return fuel system was the most impactful single application of that philosophy in his career. But it wasn't an isolated decision. It was consistent with how he approached every aspect of the car. Find the root cause of a problem. Solve it at the root. Don't add corrections on top of a broken foundation. The return system was the most elegant expression of this thinking, but the thinking itself permeated everything the Glidden team did. Let's talk about the science at a slightly deeper level, because there are aspects of why this works that go beyond the straightforward pressure regulation explanation and get into some genuinely interesting fluid dynamics. In a deadhead fuel system, the fuel lines behave somewhat like hydraulic pressure vessels. When demand at the carburetor changes, the change in pressure propagates through the fuel lines as a pressure wave traveling at the speed of sound in the fluid, which for gasoline is roughly 1,100 meters per second. That sounds fast. and over short distances it is fast. But at 8,000 RPM, the engine is completing 133 combustion cycles per second. The timing window for precise fuel delivery at each cycle is measured in milliseconds. Pressure waves bouncing back and forth in a deadhead system can create standing waves that alternately enrich and lean the fuel mixture at frequencies that correlate with certain RPM ranges, causing power variations that are periodic rather than random. Racing tuners used to note that some engines had RPM ranges where they ran particularly well or particularly poorly, and often attributed this to carburetor or ignition issues when it was actually a fuel system resonance phenomenon. A return system nearly eliminates this by preventing the development of standing pressure waves. The bypass regulator provides a pressure relief path that absorbs pressure wave energy before it can reflect back through the system. The continuously moving fuel in the rails doesn't allow pressure to build in the localized areas where resonance effects concentrate. The fuel rails in a return system behave more like an infinite pressure reservoir and less like a resonant chamber. At RPM ranges where a deadhead system might show periodic power variation due to resonance, a return system shows flat, consistent behavior. Glidden probably didn't know the fluid dynamics terminology for this effect, but he almost certainly observed it in dyno testing. The flat, consistent power curves that his return system produced compared to the somewhat peaky and variable curves of deadhead systems were unmistakable on paper. And if you can see an effect consistently on paper, you can design around it even if you don't fully understand the mechanism causing it. That's empirical engineering at its most effective. The evolution of return fuel systems in the decades following Glidden's breakthrough is a fascinating study in how an innovation matures and spreads through an industry. In the first few years after 1986, adoption was primarily within professional motorsports. The systems required fabrication skills and tuning knowledge that were beyond most amateur teams. The components were expensive relative to conventional fuel system parts, and the consequences of a poorly executed installation were serious enough to discourage casual attempts. By the early 1990s, aftermarket manufacturers had developed complete bolt-on return system kits that significantly lowered the barrier to entry. Aeromoda's products in particular made return systems accessible to the serious weekend racer and performance street car builder. Weldon pumps produced high-quality mechanical pumps specifically designed for return system applications. Holley, which had been a dominant carburetor manufacturer, began developing pressure regulators optimized for return system use. The industry had recognized that Glidden's concept represented the future and started building the infrastructure to deliver that future to a broader market. The transition to electronic fuel injection accelerated adoption exponentially. When manufacturers like General Motors, Ford, and Chrysler started equipping their performance vehicles with EFI as standard equipment, through the late 1980s and into the 1990s, every one of those systems was a return-style design. The Corvette's tuned port injection system, which debuted in 1985, used a return system. The Mustang's fuel injection used a return system. Every factory turbocharged and supercharged car, where stable fuel pressure is even more critical than in naturally aspirated applications, use return systems. The technology moved from being a secret competitive advantage in pro stock to being the baseline design expectation for any serious field delivery system in under a decade. Modern applications have extended the concept into territory that would have seemed like science fiction in 1986. Direct injection systems, now common in both performance and economy-focused automotive applications, operate at fuel pressures between 1,500 and 3,000 psi. At those pressures, a deadhead system wouldn't just underperform. It would be physically incapable of maintaining stable conditions because the compressibility of fuel becomes significant at extreme pressures. Return systems at these pressures are not just beneficial, they are mechanically necessary. The high-pressure pump that delivers fuel to the injectors is fed by a low-pressure transfer pump running at conventional return system pressures. The high-pressure pump oversupplies the injectors, and a high-pressure bypass regulator returns excess fuel to the low-pressure side of the system. The concept is layered, but the foundation is exactly what Glidden built in 1986. What does all of this mean for you if you're building a performance car today? Here's the practical application of everything Glidden figured out, distilled into what actually matters for real-world builds. Whether you're running a carbureted street rod, a boosted engine management system, or a modern EFI platform on a track car, the principles are identical, and the decisions you make about your fuel system will have cascading effects on everything else in the build. For carbureted applications, which still represent a significant portion of the performance and drag racing community, a return system is no longer optional for serious performance. It's the baseline. Here's what most people don't realize about carbureted return systems that differs from the EFI version. Carburetors are sensitive to excessively high fuel pressure in a way that EFI systems are not, because the carburetor relies on a float and needle valve to control fuel entry into the float bowl. Too much pressure overwhelms that needle valve and floods the engine. A properly set up carbureted return system typically targets between 5.5 and 7 psi at the carb inlet, depending on the specific carburetor model and its needle valve size. The bypass regulator is set to this pressure, and a return line handles whatever the pump produces above this threshold. Getting this pressure setting right is critical. Too low and you'll see lean conditions at high demand. Too high and you'll fight flooding at idle and part throttle. For boosted applications running either a turbocharger or a supercharger, the return system concept gets a critical refinement that Glidden actually touched on in his later development work, though the terminology has evolved since his era. On a boosted engine, the fuel injectors or carburetor are seeing inlet air at elevated pressure, which means the effective pressure differential across the fuel system changes with boost level. A 15 psi boost application has 15 psi of pressure pushing back against the fuel system that a naturally aspirated engine doesn't have. If your fuel rail is at 43 psi and your boost is at 15 psi, the injector only sees 28 psi of differential pressure, not 43. To compensate, boosted applications use what's called a rising rate regulator or a manifold referenced regulator. This device connects a reference line from the intake manifold to the bypass regulator's spring side. As boost pressure rises, the reference pressure pushes on the spring side of the diaphragm, requiring higher fuel rail pressure to open the bypass cord. The result is that fuel rail pressure rises proportionally with boost, maintaining constant differential pressure across the injectors regardless of boost level. This is a direct evolution of Glidden's concept, adding one input variable to the regulator's control logic without changing the fundamental operating principle at all. For modern EFI applications on standalone engine management systems, the return system is simply non-negotiable, and most people building these cars understand that. What they sometimes miss is the importance of the return system's capacity matching. Your return line, your bypass regulator, and your fuel pump all need to be sized correctly for each other. A pump that dramatically oversupplies the engine and a regulator that can handle the full bypass flow will give you outstanding pressure stability. A pump that barely meets maximum demand with no excess capacity will cause pressure drop under peak load because the regulator has nothing to bypass. The rule of thumb most experienced builders use is to size your pump for approximately 125% of your anticipated maximum fuel demand, leaving 25% of pump capacity as continuous bypass flow even at maximum engine load. This ensures the regulator is always bypassing something and therefore always in active pressure control. Here's what most people get wrong even when they understand the return system concept. They focus on the regulator and the pump and then run their return line too small. A return line that's too restrictive creates back pressure against the bypass regulator, which causes the regulator to see elevated downstream pressure and regulate to a higher pressure than it's setting. A half-inch return line is the minimum for any application that's moving meaningful fuel quantities. 3/4 inch is better for high horsepower applications. And the routing matters as much as the size. Every fitting, every bend, every length of line adds restriction. Minimize fittings. Use sweeping bends rather than sharp angles. Route the return line away from heat sources. These are the installation details that separate a return system that works perfectly from one that works most of the time but has mysterious pressure stability issues under specific conditions. The tank fitting where your return line re-enters the fuel cell is worth specific attention, and this is something Glidden got right in 1986 that many modern builds still get wrong. Return fuel entering a tank or fuel cell creates turbulence that can aerate the fuel and draw air bubbles into the pickup. For short drag racing applications where you're only running for a few seconds at a time, this matters less. For road racing, endurance racing, or spirited street driving on a car that sees sustained high-performance use, aeration is a real concern. Return fuel should enter the tank below the fuel surface level, not above it. It should be directed away from the pickup through a baffle or by routing the return fitting to the opposite end of the tank from the pickup. a simple internal baffle that separates the return area from the pickup area, which is exactly what Glidden built into his fuel cell, is one of the highest value low-cost additions to any performance fuel system. For anyone building a period-correct 1980s Pro stock tribute car, or just trying to understand what made those cars tick mechanically, it's worth noting that Glidden's original system can be replicated with entirely period-correct components that are still available through specialty suppliers. The Hilborn pump design hasn't fundamentally changed because the spur gear pump is still one of the most reliable and flow-consistent designs available for mechanical fuel pump applications. The bypass regulator concept is well understood enough that multiple manufacturers produce regulators with characteristics very close to what Glidden developed empirically. The aluminum fuel rail construction is standard practice in any serious build today. There's nothing in Glidden's 1986 system that requires exotic unobtainium parts or proprietary components. What it requires is understanding why each element works the way it does, which brings us back to the lesson that runs through this entire story. Bob Glidden won 10 NHRA Winston Pro Stock Championships. He won 85 national events. He drove his last professional race in 1997, and by that point he had earned a place in the conversation about the greatest competitors in drag racing history. He passed away in November 2017, and the tributes that came from across the motorsports world reflected not just appreciation for his driving ability, which was exceptional, but specifically for his engineering mind. Competitors who had spent years trying to beat him talked about how he made everyone better by forcing them to innovate faster. The engineers and major automotive companies who had quietly studied his fuel system work talked about how his empirical approach had validated concepts they'd been theorizing about in development programs. The weekend racers who built their first return systems using parts that only existed commercially because of what Glidden had demonstrated talked about how different their cars felt afterward. Here's the thing about truly impactful innovation. The measure of it isn't how famous the innovator becomes or how much credit they receive while it's happening. The measure is how completely the innovation becomes invisible once it's been adopted universally. The highest compliment you can pay to a technical innovation is that people forget it was ever innovative at all, because it has so thoroughly become the only way anyone thinks about doing the thing it improved. Nobody building a modern performance EFI system debates whether to use a return system. It's simply what you do. Nobody designing a factory turbocharged production car considers a deadhead fuel system. It's simply not how it's done anymore. The concept has become the baseline, the assumed starting point, the thing that you build from rather than the thing you build toward. That's where Glidden's innovation lives now, invisible in the best possible way, baked into the fundamental architecture of every serious fuel system on the planet, present in your daily driver, in the NASCAR car on your television on Sunday afternoon, in the Formula One car running a fuel injection system at pressures Glidden never imagined, in every corner of motorsports and automotive engineering where fuel gets from a tank to an engine with the precision and consistency that modern performance demands. The farm boy from Indiana who moved to Oklahoma and spent his evenings in a small shop asking questions that nobody else was asking changed how every car on Earth manages its fuel. He did it without a corporate budget, without an engineering team, and without any of the resources that modern development programs take for granted. He did it with first principles thinking, hands-on experimentation, and a willingness to look at a system that everyone accepted as functional and ask whether it was actually as good as it could be. It wasn't. He proved it. And 40 years later, the proof is in the fuel system of every car you've ever driven. Drop a comment below and tell me what other overlooked engineering innovations from motorsports history you want to see covered. The ones that never made the headlines but quietly changed everything are the stories I want to tell, and your suggestions genuinely shape what comes next on this channel. If you found this breakdown useful, the subscribe button and the thumbs up help this content reach more people who care about the engineering behind the machines. Until next time, remember that the most important question in engineering is often the simplest one. Not how do we do this better, but why are we doing it this way at all?